Okay, so let's talk about this week plan. We're having a test on Friday. So that test will be on volume and area between curves and polar. So that. Today we're going to talk about how to find area in polar, and you will have a delta math assignment tomorrow. You'll have one out of the book today, but a delta math assignment tomorrow to help you practice that. And that's good because it'll be like an immediate feedback kind of thing. So like instead of me giving you a quiz over polar before the test, which I would like to do, the delta math will serve kind of like that purpose. So you'll get the feedback to know that you're getting it right. Yeah. So we have questions about that? Questions about the homework? Yeah?
161. It's 3x minus y equals 2, and it's asking to convert it to polar.
3x minus y equals 2, and then it says convert that to polar. 3x minus y equals 2. So convert this baby to, this is 161, Meg? So convert that to polar. Is that what you want us to do? Okay. So the only thing we really can do right now is just be like, okay, well, 3 times r cosine theta minus r sine theta equals 2. It looks like I could factor out an r out of this. And then it looks like I could probably divide. And that's probably as good as we can do. So what is 3x minus y and 2? If I were to graph that in Cartesian, what is that? Like, what does the graph look like? It's a line, right? It's a linear. Okay, so this must be one way of looking like a line in polar. Maybe. Maybe not. Maybe it's not a line. What happens if you graph that in polar? Is it a line? Does that help?
This next one, 162, it's y squared equals 4x, but it's asking
Y squared equals 4x. Convert that to polar. So r squared sine squared equals 4 r cosine theta. So now if I divide both sides by r, which is a potential problem, but if we want to get this solved for r, we would have r sine squared theta equals 4 cosine theta. And then r equals 4 cosine theta over sine squared theta. Oh my God. I wondered whose that was during first period. I almost gave it to a kid. Someone didn't have their Chromebook. I was like, well, whose is that back there on the thing? Other ones? Yeah. Other questions? We good? So we're happy with polar graphing, sort of? Yeah.
So the ones where we have to sketch a graph, can we look at this?
Absolutely. Yeah. I don't know that I find it beneficial for you to memorize what these graphs do. I personally don't have them ingrained in my memory. I mean, the only ones I know about are the flowers, but like I can't remember like with limicons and cardioids. Like I can't remember what the ratios of the constants are. So I'm not too concerned with that. Yeah.
So are we going to use decimals on our test further?
Of course. Yeah. Oh. Okay, so let's talk about area then. So what we want to do is figure out a way to find, like, say for example, if you had a polar curve that looked like this, how could we maybe find the area of this? Of that leaf. Okay, so that's what our sort of goal is. So we're going to use integration to do this, and we're going to develop this formula just so you can see where it comes from and see what it is that you're adding up. Okay? So in order to get there, we got to go back probably to freshman year. If I gave you a circle, and I said, find the area of that piece of pie, like that little piece of the pie, you guys think you can do that? From that? Or more? Yeah, from that. Well, I mean, I guess I could give you a theta value and an R value, but could you just tell me what it is in terms of R and theta? So you don't remember the formula, which is fine. But you could probably reason yourself into the formula, as long as you know how to find the area of a circle. How do you find the area of a circle? Pi r squared, right? Well, what fraction of the circle is that? Theta is the fraction. Theta over 2 pi. Or probably back in geometry, it was theta over 360. Right? If you did this in geometry class, they would give you this angle, and it was, oh, that's that fraction of the circle, because the whole circle theta would be 360, right? But Ross tells us the area of that sector, that's what that's called, which is the piece of pie, is theta over 2 pi times pi r squared. Theta over 2 pi is the fraction of the whole circle, right? Which means these pi's, I guess, would cancel, so that would be theta over 2 r squared. Or 1/2 r squared theta. Okay? So that's the area of a piece of pie of a circle. You guys agree with that? Okay, so now what we're going to do so close, but yet so far away. So now what we're going to do is we're going to think of this piece of polar area here, this leaf. I'm going to think of that. I'm going to break that into pieces. And I'm going to say that angle right there is delta theta. Okay? And I'm going to pretend, just for right now, that, can you guys see that green thing? Okay? I'm going to pretend that green, for a really small value of delta theta, that green wedge is like a piece of pie. Okay? It's like a piece of pie where the R is changing. It's like a sector of a circle where the R is changing. But if I make a really small delta theta, there really won't be much change in R. Right? So what's the area of that piece? Well, apparently it's 1/2 R squared delta theta. Because delta theta is the angle. It's just like one of these guys over here. All right? So an approximation of the whole area would be just sum up a bunch of those guys, right? But how do you make that approximation better? What do you do in order to make that approximation better? What do we need to do? Well, that's what happens by when we make it really good. How do we make it better before we integrate?
Try to make those slivers get
Right, make the delta theta get really, really, really small, right? So if we take the limit as delta theta goes to 0 of all this, that's when we get the exact area. And that's where we get this formula, 1/2 R squared d theta. And then all you got to do is just say, okay, well, where am I summing these up from? And instead of using A and B, I'm going to use alpha and beta. Now, why am I using alpha and beta instead of A and B? That's a terrible looking alpha. Looks like 9. Why am I using alpha and beta instead of A and B? Because alpha, we typically use Greek letters to represent angles. Theta is like the x, right? I mean, x is our go-to variable for pretty much a regular old real number. Well, theta is our go-to variable for an angle. And then once you've used theta for something else, then we just start using other Greek letters. And we just started with A and B. Okay? So that formula right there is how you find out the area that's swept out by a polar graph. Okay? You just got to know the values of theta or the bounds of theta that will sweep out the area that you're wanting. Okay? So for example, in this leaf right here, as we increase theta from alpha to beta, we should sweep out that curve. Okay? Finding the bounds is the hardest part. Right? Now I'm just curious, last year, do you remember doing problems where you would be given polar graphs and the problem would say something like, okay, find the values of theta that will make this part of the graph, where it's like a moon shape or the part inside the inner circle. That's why you were doing those problems, was to set you up for this. All right, let's do some problems. This is a formula that we got to memorize. But again, understand, what are we adding up here? What is it that we're adding up in order to find that area? What is it that we're adding up? Small pieces of pie. Or small sectors of circles with changing radiuses. Okay, I like piece of pie better. Okay, I actually would rather these be pizzas, not pies. I'm not really a big pie person. Unless it's a pizza pie. Okay, so you ready? So let's do an example of like the one we just did. So I'm going to give you a R equals 4 sine of 3 theta. And your task is to find the area of one leaf. Now you might want your Desmos here so you can play around with bounds. Okay? So find the area of one leaf. So I'll pop a Desmos up here on the board. Oh, and you know what I've discovered is you don't actually have to change the grid to polar. You can graph in polar without changing the grid to polar. I didn't realize that. All this time, I've been using Desmos. 4 sine of 3 theta. Okay, so one way of doing this, to find the area of one leaf, one way of doing this would be to find the area of all 3 and then just divide by 3. Okay? But we want to be a little bit more strategic in that because I think it'd be more fun to find the values of theta that will sweep out one leaf. Okay? So can you guys do that? What are the values of theta that will sweep out one leaf? How do we do that algebraically? I mean, you could just start guessing on your, just typing in various things until you see one leaf. But what's the strategery in order to do that? If we're going to sweep out one leaf on this, okay, if it's going to go like this, what is R when we start and stop that leaf? 0. So let's algebraically find out what values of theta make R 0. So we're going to solve that trig equation there. 0 equals 4 sine of 3 theta. So now we got to know our unit circle pretty good here. We got to know, where is the sine 0? Well, sine 0 at 0, pi, 2 pi, 3 pi, etc., right? So that equals 3 theta. So theta then is 0, pi over 3, 2 pi over 3, 3 pi over 3, etc. So what values of theta are going to sweep out that loop in the first quadrant? What values of theta are going to sweep out the loop in the first quadrant, or sweep out the leaf in the first quadrant? 0 to pi over 3? Okay, try that just to verify. We good? Did you get one leaf? Sweet. So that means the area of that one leaf is going to equal 0 to pi over 3 of 1/2 r squared. But what was r? Question.
On the test on Friday, are you just gonna have us find the integrals, or are you gonna have us solve it?
Are we going to, so I was just about to say, how do we feel about computing that? Nobody wants to compute anything. I turned you guys into a bunch of lazy bums, right? Just, oh, just worry about the setup. Yeah. Okay. Most of these we're going to leave as is. Okay. Just as the setup. I might have you compute one, and it won't be any more complicated than that. Okay. And the reason why I'm going to make you, might make you compute that one, is it involves anti-differentiating sine squared. Which, if you remember, we've been tested on that before. Okay, it's just good to know the antiderivative of sine squared or cosine squared. So the most you would ever have to do is 1. All right. Can we do that? Yeah. Let's actually, let me go through these other examples first, and then if we have time, we'll come back. And then if we don't have time today, I'll do it tomorrow. So questions on that? Yeah.
Would you, like, since you just said find the area of one leaf, could you do like a different bound so that it is in different quadrant?
You mean and get a different leaf? Yeah. Now sometimes you might be told specifically which leaf we're after. Like, so if I said find the area of the leaf that's in the first quadrant, then you'd have to give me that one. If I said any leaf, then you could give me really almost any two of these angles back to back would trace out a leaf. Okay? Well, that may not be true. Actually, I think. All right, let's do another one. So I'm going to give you two curves on this one. So I want the area that's inside the circle, but outside the cardioid. All right, so we'll go to the Desmos. Go to the Desmos. R equals 2 plus 2 cosine? Yes. I actually had these typed in here ready to go, and then I accidentally erased them last period. Six cosine. Okay, so you see the two curves? One of them is a cardioid. Which one do you think is the cardioid? The one that's not a circle, or the one that looks like a heart, or a butt. Some people think they look like butts. Okay, so it says the region that's inside the circle but outside the cardioid. Inside the circle and outside the cardioid. So that looks like that moon shape right there. Okay? So where do we start? What's the first thing that you would think that we should do? Find the area of the whole circle. And then what? So find the area of the whole circle and then subtract the area of the whole cardioid. Is that what you're saying? Can I do that? Will that work? Why not? Why will that not work? I almost believed it for a second, but then I caught myself. Because that's not what I was expecting you to say when I asked that question. Why will that not work? Why can I just not find the area of that whole circle and then subtract off the area of the heart? What?
Because the heart's not entirely.
Right. The cheeks. Right? I would be subtracting that out, and I don't need to. Okay? I will tell you this, though. To do this problem, this particular one, we cannot do it with only one integral. We actually have to find two areas and subtract them. So what do we think we should do now instead? If this were not polar, what would be the first thing that you would do? If I asked you to find just the area between two curves in regular, what would you do first?
Do the two lines and then subtract the.
Yeah, but before you even do that, there's something we got to know. I think that you're just assuming that we do know, but I haven't told you. What's the thetas where they intersect, right? Like, what are the theta values? Like, I don't know what these angles are here. Okay, and sadly, Desmos doesn't tell you. Like, you can't just click on it and it tells you, like, it does in part B. Dang it. That's Bush League. Might as well throw this thing away. So it looks like you're going to have to do that algebraically, yeah? Okay, so solve that equation for me. Solve it as far as you can, and then stop. Did you get to this point? So again, we got to know some trig here. It's nice when these come out to be special angles. I think it's harder when they're not special angles. So where is the cosine equal to 1/2? Where's the cosine equal to 1/2? Pi over 6 or pi over 3? One of those two, isn't it? It's pi over 3. So theta equals pi over 3. Now we've got to know how this works here. It's not just pi over 3, because there's lots of places where the cosine is equal to 1/2. What quadrants is cosine positive in? First and fourth. Right? First and the fourth. So that's pi over 3 and 5 pi over 3. Right? So pi over 3 and 5 pi over 3. All right. So let's do something here before we, just get all jacked up here. Let's go ahead and say pi over 3 and 5 pi over 3 So I actually, I don't know if you guys saw what I did. Maybe you all weren't looking. But I actually just went to the cardioid first, and I typed in pi/3 to 5/3, and I turned the circle off. So let me show you something here. If I were to change theta from pi/3 to 5/3, this is what I'm going to get. I'm going to get this area right here. Okay? Does everybody see that? Could I use that area potentially? Maybe. But what happens if I change theta from down here and then increased it to right there? What part of the cardioid am I going to get then? I'm going to get this part inside. Okay? So what value of theta do I need to be the top one? The upper bound for theta. This is where you got to understand your trig. Okay, now there's a few ways we can do it. One way of doing it would be dealing with positives and negatives. That'll work. Okay? And another way of doing it would just be to going past 2 pi. Okay? So if I start at 5 pi/3, and then I go past 2 pi, I need the angle that's coterminal with pi/3 in the first quadrant, but it's past 2 pi. What is that? 7 pi/3. Not 74. Okay, so now do you see the part of the cardioid that graphed? Okay, you might want to look at your screen because I've got these other things drawn on here. I don't need this anymore. Oh. Now, just so you can see that, can you think of another way that we could have done that in the fourth and the first quadrant? Maddie, what were you going to say? Negative pi/3 to pi/3. That would also do it. Okay? So, now, this big, huge wedge here is what needs to be taken out of the circle. Right? What needs to be taken out of that big wedge. Okay? So find the area or find me the bounds of theta that will give me that big wedge. And this one's going to be a little goofy. Okay, so watch this. I'm going to turn the other one off. We know we got the bounds on the cardioid, what we wanted. But the circle is going to be a little goofy. If I use the same bounds here, well, that did work. Oh, it worked.
Can we do it in one then?
So we could do it in one. All right, so let's write it. Or let's write it in 2 and then see if we can combine it to 1. So the area of the big circle is going to be from 5 pi/3 to 7 pi/3 of 1/2 6 cosine theta squared d theta. That's going to be the area of the big wedge. And then we're going to take out the cardioid wedge from 5 pi over 3 to 7 pi over 3 of 1/2 2 plus now the second integral is one that I would never have you compute that by hand. I don't want you to have to FOIL that out. It just gets ugly. Back in my day when I took this, like we had to do those, it was awful. I'm not going to subject you to the same torture. Okay, so could you write it in 1? Sure. And just to show you how Maddie's angles work too, I'll change the bounds when we write it in 1 just to make it look cleaner. So negative pi over 3 to pi over 3 of 1/2 6 cosine theta squared minus 1/2 2 plus 2 cosine theta squared. All d-thetaed. Okay. So there are multiple ways that you can get these angles. In fact, when I worked this out this morning, I actually did it a totally different way. I didn't even think to try those bounds of 5 pi over 3 and 7 pi over 3 on the circle. And the reason for that is because I knew right away when I started it that the circle only went 0 to pi. Right? 0 to pi traces out that whole circle. And so I was like, oh, that's going to mess me up. So I just treated the circle totally separate. And I calculated the bounds of the circle first. Then I did the cardioid. Questions on that? We almost got it. Okay, what about the end? Let's do one more. Let's at least get one more set up. What if I gave you this? R equals 2 plus 4 sine theta. And I said graph the inside loop. It actually looks like this, but I want just the area of the inside loop. So we got to find the values of theta that will trace out that inside loop. Well, we set R equal to 0. And you end up getting sine theta equals negative 1/2. So what quadrants is the sign negative in? Third and fourth. So it's the pi over 6 family in the third and fourth. So that's 7 pi over 6 and 11 pi over 6. Those are your bounds that you'll use. So I'll go ahead and tell you what your homework is. I'll put it on the Google, but it's 7.4, 188 to 199, and 212. Set them up only. Only set them up. This is going to take you some time. Okay? Use your Desmos. And again, you're only setting them up. And have a nice day.
I remember this last. I like finding
And the butts.
yeah.
Yeah, if you can do that, then you can do the calculus. That's just the formula.
So how do you do the bounds, like the 5 pi over 3 and 7 pi over 3?
What do you mean?
I kind of got that, but didn't fully understand when you went to like the 2 pi and then adding that.
So this was, it was cosine theta equals 1/2, right?
Yeah.
That's where we got. So where's the cosine positive? That's what you're
1
gonna.
and 4.
So the first and the fourth quadrant, right? Here and here. So what's the reference, or like where's cosine equal to 1/2? It's pi over 3.
Yeah.
So what you had to do was I needed the angle in the fourth quadrant that was at a reference angle, or that was in the pi over 3 family,
Which is 5 pi.
which is 5 pi over 3.
Yeah.
Okay? So now I've got this angle down here. Now the problem is if I went from here to there, I got the back half of the graph.
Okay.
I needed this front half of the graph. So the way that you did that was you have to start at this angle and then stop at this angle. So this is your theta min.
Okay.
So I started at 5 pi over 3, and then I went to, I can't go from 5 pi over 3 to pi over 3 because that's out of order.
Mm-hmm.
So you have to give me something that's coterminal with pi over 3 that's in the first quadrant, which would be 7 pi over 3. But equivalent to doing that is going from negative pi over 3 to pi over 3.
That was kind of confusing to me, but I'm just gonna do it the first way.
Yeah, these are both equivalent.
Yeah.
Why can't you just do pi over 3 to 5 pi?
Because pi over 3 to 5 pi over 3 gave you the back half of the graph. Like,
You need the part between those two angles.
so like, was this the cardioid? Yeah, so like pi over 3 to 5 pi over 3 is going to give you this part. When I wanted this part
I
over
thought it
here.
was gonna give you like pi over 3. It doesn't not, because isn't that pi over 3 right
This
there?
angle is pi over 3.
But if you start at pi over 3 and go towards 5, if you start here and go towards 5 pi, you go that direction.
Yeah,
right?
so it's gonna trace out, it's gonna sweep out
That part.
this part of the graph. You got to think about like when you're thinking about polar area, and as you change theta, it's sweeping out the graph. So like as I increase theta from pi over 3 to 5 pi over 3, it sweeps out the cheeks of the bud, right? Whereas that's not the area that I wanted. I wanted the back half of the bud. I guess it's, I'm not really sure, but I wanted this part over here. Okay, like I wanted this part over here, so I have to start theta here and stop theta there. Does that make sense?
I should just give them the test from last year. I still have them on computer.
I don't know, I'll turn it off and give it to the submitter, see. If you get one.
It's challenging. Like
It is.
I don't know how the hell you do this without a graphing calculator. Like when I did this, I made it all up. There's no way I knew all this. There's no way I figured all this out. I would put bounds on the integrals and like get half of it wrong because there's no way you can. How do you do all that without being able to visualize it? I mean, having that helps a ton.
Yeah, it does.
Like,
Did you get the homework? Did you get it? No. So, you get a piece yesterday for Alan Clark? Yeah. What was it?
Exactly like the one where it's just like theta equals whatever. Like I didn't know how we were supposed to solve it.
Yeah.
It was also like midnight. Also, that wasn't a test. Like they were all like, "Want to get a test?" They're like,
Like what? How do you keep? What is the most? I know my part is frequent time that patient calls. Is it like what type of care? The questions that they like. If a person's
yes, they're so
conversation,
Hi Sam, how are you? Sam, you know you take lessons down.
or like how do you
Free doors have regular drive.
So,
I like.
yes, thank you. Remember the last night? If you're facing her house,
So whatever.
there's a two-story right next to her.
I'm 10.
No. One story right next to
Yeah,
her.
oh my gosh.
Another two-story, and then a split level. We're in this, that's her split level right there. I see you get dropped off every once in a while. I'm like, yeah. Is she good?
I think I
It's
what
so-
about her?
Oh, nice, nice. She did a couple of outdoor, because it's such a little impromptu little concerts that are
Right behind the steering wheel.
this summer with COVID, it was really nice. Neighbors just came out and sat around and.
Yeah, 'cause mine had a little like 105 here.
No, mine.
Have a good day, everyone. Thanks for stopping dinner.
Yeah.
I turned it off, there's a little bit.
You didn't turn it off, I did.
Yeah. Oh, you did?
I just did, like.
Well, I think I should turn it off because I was like, I forgot to. I guess I must have.
I was gonna come back in.
Yeah. We did some of mine, that was
Nope.
on the tire. Have a good day.
Absolutely, see ya.
It's got 220,000 miles on it.
What has 220,000 miles?
My car.
Wow, what kind of car is it?
That is an 800 Pilot. Because we drove to Colorado in the back.
Honda Pilot, 08, is that kind of the ones that are boxier?
Yeah.
I like those better. We have a Pilot, and I like the boxy ones. They're more sporty. Ours looks like a mom car.
I like it. The only thing I don't
No,
like is that
Yours
it's white.
does look like a mom car, but it's a nice mom car.
Yeah, I mean, it looks totally like a mom car, but
Yeah.
I like the boxy ones.
The only thing I don't like about it is it's white and it gets dirty super easily,
Hmm.
which I don't like. And it doesn't get good gas mileage, and like, I have to drive like,
It gets way better gas mileage than my truck.
well, yeah, because I have to drive to Indiana for practices like twice a week.
What, practice for what, soccer?
Soccer, yeah. Because my practices are like 10 minutes away from Perfect North. It's not that far, but it's so far.
What team do you play?
We're called the Tempest Shockers. We're out of like that like circle where it's like Kentucky, Ohio, and Indiana, like that corner. Yeah. So it's like right there. But technically right in Indiana.
Mama, that's far.
Yeah.
All right. Well, here's the plan for the week. Nicole, I feel like you're just way over there by yourself. And if you are over there by yourself, it's like you want to be quarantined over there by yourself.
I don't know. I don't really mind.
So the plan for the week, okay, so we're still on a test on Friday, yes, and that test is going to be over area between curves, it's going to be over volumes, and it's going to be over polar. Today we're going to learn how to do polar area, and you'll have some problems in the book on that, and then you will have a Delta Math assignment tomorrow on that you'll do on tomorrow and for Wednesday. And that's going to be like kind of a quiz for you for polar area so that you know how to do it before the test. Normally I would give you a quiz on polar area before I tested you on it. However, with us not having school on, well, let's just face it, us not having school on Wednesday, I'm not going to give you that test on Thursday when we have a test on Friday. That's silly. So Delta Math can kind of help with that, because that way you can get some immediate feedback. Oh, yeah, I got this right, or no, I still don't know. Okay. The questions on your homework from last night. Yeah.
So I found a question for about, I can't, what if 1, 3, 4 to 1 instead of casting?
That section, like,
What is what asking now?
154 through 157.
One 60.
150.
Wow. Well, what they were asking is they were hoping that you would know what those are by heart. But I don't know. I mean, I'm fine if you just graph it and said, "Oh, that's this." Okay. You should have noticed that, like, you know, a couple of those, in fact, all but one of them were lines. Okay. The only one that wasn't a line was the circle that was number 154. But the other three are all lines. Okay? Like they're linear polar graphs. Make sense?
But I get, what is the wording on that again? I don't know. What is it?
It says describe the graph and then confirm your description by converting to a rectangular equation.
Okay, so it's just, they don't want it.
So they want you to convert it to prove that it was a line. Or prove that it was a circle.
You do 155 out of it?
Yeah, theta equals inverse, or theta equals
Pi over 4. So prove to me that that's a line. Well, we know that theta is the inverse tangent of y over x has to equal pi over 4. So then y over x equals the tangent of pi over 4. So y equals tangent of pi over 4 x. And what's the tangent of pi over 4? 1.
In fact, I mean, you could extend this a little bit. The equation of any line through the origin is y equals mx, right? M is the slope. Well, it's really also equal to y equals tangent theta times x, where theta is that angle. You know that? The slope of a line through the origin is the tangent of the angle that that line makes. And that shouldn't be a cosmic leap for us. If it goes to the origin, the slope is just y over x, right? And all you got to do is drop this perpendicular, and now you got a right triangle. Other question? Other question? Nina, you drive yourself to practice?
Yeah.
That's a long drive. I mean, you're not a super experienced. Well, you are, I guess, an experienced driver. I mean, by now, you've got more miles behind you than probably most kids your age.
Yeah, I do that twice a week, and then I do that on Thursdays and Sundays. And then on Tuesdays, I drive to Joyce Park, and I play with
Joyce Park. That's where I grew up, man. That's mine.
Yeah.
In Fairfield.
Yeah. And like Hamilton or whatever. Yeah, because I play with so like we're U17 teams, so I play with the U18 instead of driving out there on Mondays.
Joyce Park, there always used to be a big tournament there, the masked tournament.
Yeah, that's what I do.
Oh, it's coming up?
Yeah.
That's still a thing?
Yeah.
Mid-American Soccer Classic.
Uh-huh.
Oh, yeah, that's
Yeah.
like fields, I mean, they just go for miles.
Yeah, except I don't know if it's gonna happen because the guy that like paints all the fields, like none of the fields are set up because the guy that like paints all the fields and like, does that, his mom's like died.
Oh, that's terrible.
I know, it's so sad. So like,
I wonder if it's somebody I know.
I don't know.
I mean, that's where I grew up. I mean, I grew up in Fairfield. Like, that's in Fairfield.
Yeah, so like we're just like,
I used to launch rockets in Joyce Park, like model rockets. We built these model rockets.
fields are so awful. They're so terrible.
I mean, it's a humongous place.
Yeah, it's huge.
Like, I can't think of anything comparable around here that's as big as that, with that many fields.
It's bigger than Delta. It's way bigger than Delta.
Oh, yeah.
And
It's like 10 Delcos.
Like makes sense.
You drive by the Joe Nuxall batting range
Yeah.
as you're driving in.
Mhm.
Joe Nuxall was the former announcer for the Reds and the youngest person to ever play professional baseball. He went out and pitched for the Reds when he was 16 years old in 1948 or something. 16-year-old went out and pitched in the game. But his son was my gym teacher in elementary school.
How do you even get there that young? Like, were they
Well, there
watching
was something, I think it was in like 45 or 46, the war, like the World War II was still kind of going on, so they were a little short on players. But yeah, his son, Mr. Nuxall, was my elementary school gym teacher, and I went to those batting cages, and actually I went to the driving range, the golf driving range, when I was like junior in college. And Mr. Nuxall was working there, and he came up and knew exactly who I was. He's like, "You're Scott Mitter." Like, hadn't seen me since 5th grade. Like, he knew exactly who I was. Oh, goodness. Another question, all? Well, okay, let's talk about polar area then. This is so fun. This is such a good time. You guys remember last year in pre-calc doing problems where you were graphing polar and it said graph like this moon shape only, or graph the inside loop of the cardioid. Okay? The reason why you were doing those problems is really to set you up for today. Okay? Because the hardest part about polar area is really getting the bounds of the angles, the thetas. Polar area. Okay. So, like, kind of our goal here is if this is some curve, we want this area. Okay, that's what we want to do. And it's very simple how to, like, it comes down, I'm going to give you a formula. We're going to learn a formula. But we're going to develop that formula so you can understand where that formula comes from, and that you understand that integration is not just a formula. Okay? You're adding something up. So we got to figure out what it is that we're adding up. All right, so speaking of elementary school, if I gave you that circle right there, I gave you that central angle, that's what that's called, is a central angle, theta, and that circle has a radius of r. You see that piece of pie there? This piece of pizza? Could you find the area of that? Do you know how to find the area of that? Okay, now if I say, could you find it? Well, just tell me what it would be in terms of theta. Like if I gave you the angle and said that's 30 degrees or 35 degrees, could you find it? Could you find the area? How do you do it, Alex?
find the area of a circle, and if it's 35 degrees, then you just do 35 over 360.
So what is the 35 over 360 really telling you? What fraction of the circle is it? Right? So that little pizza slice is called a sector. Maybe a word that you don't remember. So if theta were in radians instead of degrees, wouldn't that be theta over 2 pi times pi r squared? This is the fraction of the circle, and then that's the area of the whole circle. And then I guess I could simplify this. The pi's cancel, and I have theta over 2 r squared, or 1/2 r squared times theta. So that's a little trip back to geometry for us. So the area of a piece of pie is just 1/2 r squared times whatever that angle is. Okay, so you actually could find the area of your next piece of slice. Yeah, the angle. You just carry a protractor around with you and then. All right? So how does that relate to what we're talking about? Well, what we're going to do here is we're going to think of this graph right here, this polar graph, we're going to think of it like a bunch of pieces of pie or a bunch of sectors of circles where the radius is changing. Okay? So let's say that this is r, okay, and then this is delta theta right there. Okay? So I could say I'm going to approximate the area of this chunk right here with pretending that that's a circle. And that's a little wedge of or a little piece of pie. Well, what would the area of that be? It would be 1/2 r squared. And then what's the angle? Delta theta. So I should say, instead of area of one piece, I should say approximate area of one piece. Because we're treating that like it's a circle. All right? The book actually refers to that as a polar rectangle. But we'll not necessarily call it that. So area of one piece is 1/2 r squared delta theta. So then I could say the approximate total area would be, well, just add up a finite sum of many of those. And that's going to approximate the area of the whole leaf. But then how do you make the approximation better? How do you make the approximation better? More pieces. And how do you get more pieces? What needs to get small? Delta theta. And really, what really needs to happen is delta theta needs to approach 0. And when delta theta approaches 0, that finite sum turns into an infinite sum. So that's the actual area. So that's a formula that you pretty much have to memorize, okay? But understand what it is that you're adding up. In this particular case, now we're adding up basically an infinite number of slices of pizza that the radius is changing in size. Okay? Now, what are alpha and beta? Those bounds. Okay? What are the bounds that we're talking about here? Alpha and beta. Those are the theta values where you start and stop. That will sweep out the particular polar area that you're looking for. Okay? So whatever theta is right here, and as you increase theta, to right there. You would sweep out that area. Okay? I actually sometimes like to think about my polar area as like, is actually sweeping out a bunch of radii over that are changing in size, and they're all together. Okay? Why is it alpha and beta and not A and B? Because we typically use Greek letters to represent angles. That's why. Okay. Like x is your go-to variable for a real number. Theta is your go-to variable for an angle. But when you've already used theta for something else, then you go to A and B, alpha and beta. Right? All right, so you ready to look at this with some real problems? So, example number 1, r equals 4 sine of 3 theta. Find the area of one leaf, or one petal. So you're probably going to want your Desmos. Everybody loves the Desmos. I just learned something this morning. You don't have to change the grid on Desmos to polar to graph in polar. I never realized that until today. So I want the area of one petal. Now, one way that we can do this is to find the area of all 3 petals and then just divide by 3. Okay, that's one way of doing it. But I want to do it to where I'm sweeping out only one petal. Okay, so the first step in any of these problems is to figure out what the bounds are. Okay, what are the values of theta that are going to give us the area that we're looking for? All right. So what we have to do is figure that out. Okay, we have to sort of figure it out algebraically. In fact, Desmos won't let you even trace in polar, so like you can't pull these off of the computer. You actually have to figure them out. So in this thing, what's R when we start and stop a pedal? What's R? 0. So let's algebraically solve that equation. So you got to know your trig here, all right? It's really, I think these are easier when they're special angles, when they're on like special angles that we know. These problems are much harder when they're not special angles, I think. So you got to say, okay, where is the sine 0? What angle has a sine of 0? Well, that's 0, pi, 2 pi, 3 pi, etc. Right? So that has to equal 3 theta. So what's theta? Well, divide those all by 3. 0, pi over 3, 2 pi over 3, 3 pi over 3, etc. Okay. So now, if we just look at the first 2 of these and say, okay, what happens if we increase theta from 0 to pi over 3? Does that get the part of the graph that we're interested in? So just go to your Desmos. You can find your mouse. And I'm going to go from 0
pi over 3. That gives me that leaf. Yeah.
Since Desmos defaults to 0 to pi whenever you type in a polar graph, and it has 3 leaves, can you just use that?
So that is using your brain a little bit. And in this case, that worked. I don't know that that's always going to work, but absolutely. Okay, that definitely does work in this case. Okay? So now, we got our bounds. So the area of one leaf what was r? It's 1/2 r squared d theta. So r was 4 sine of 3 theta squared d theta. So that's the area that's swept out from 0 to pi over 3. Okay? Most of these problems that we do, we're just going to set them up and stop. Okay? If I have you compute one of these, it will not be any more difficult than this one. Okay? I think you should be able to compute this one by hand. And the reason for it is because you have to integrate sine squared. And sine squared is one that I tested you on earlier. It's just one that you should know how to do. So if we have to do one by hand, it'll be no more difficult than this one. All right? And tomorrow I will work that out by hand just to show you how to do it. But I want to make sure we get to these other examples. Okay, questions on that? Okay, that one's not too bad. All right, let's try this one. R equals 2 plus 2 cosine theta, and R equals 6 cosine theta. And the area that we're looking for is, find the area inside the circle, but outside the cardioid. Inside the circle and outside the cardioid. All right, so go to Desmos, and let's just graph both of those. And Alex, actually, Desmos doesn't default to 0 to pi. It defaults to whatever. It somehow knows, it's been programmed to know what will trace out that whole graph. And what's the other one? I forget. All right, 6 cosine? Yeah, 6
Yeah.
cosine. Oh. Yeah, that one only goes 0 to pi. Okay, so you ready? So you have to understand what area that we're looking for here. Inside the circle, which is the purple one on ours, and outside the cardioid. So we're talking about this moon shape. Okay? We're talking about that moon shape. That's the area that we're looking for. We might not be able to do this with one interval. Okay, in fact, I actually like to set them up as 2 and then write them as 1 if we have to, or if we can. But now, can you see that this is really, to find the area of that moon shape, it's really subtracting 2 existing areas. Okay? Let me show you which areas that it is that we're subtracting. Okay? In order to get this moon shape, we're going to subtract off the area of the big chunk of the circle minus the area of the chunk of the cardioid. Okay, that's what we're going to do. So the question is how do we get those chunks? What's the first thing that we probably need to figure out? The bounds. And how do we do that? Do what? Solve what algebraically? What do you mean? Are we going to set these equal to 0? Yes, we're not going to set these equal to 0, are we? Because if we were to equal to 0, the curve would be down here at the origin. And that's not the curve that we're wanting. What do we want to do, Mia? Set them equal to each other. Okay? Can't just click on it like in Cartesian and Desmos. You got to straight up solve this old school. So 2 equals pho cosine theta. So 2 pho equals cosine theta, or cosine theta equals 1/2. And now, friends, you really got to know your trig here. Now, you really got to understand your trig. Where is the cosine equal to 1/2? Okay? And you need to know beyond the first quadrant. It's positive 1/2. So what two quadrants is is cosine positive in? The first and the fourth. Cosine's negative in the second and third. Okay, so we need angles that are in the first and the fourth quadrant. Okay? So what's the first angle that we're going to come up with? Well, where's the cosine equal to 1/2? We should know that. Maybe we don't remember. What is it, Samuel? Pi over 3. Okay, so I'm going to draw a little picture over here. Here's pi over 3. Okay? Give me another angle that's in the fourth quadrant who's in that family. Negative pi over 3. Okay. That's not the angle that I was thinking that you were going to give me. And we're going to use that. But I was thinking that you were going to give me what Mia's about to give me, and that was 5 pi over 3. Okay? Now, here's what I want you to see. You might think that the two angles that we found, pi over 3 and 5 pi over 3, those are what we're going to use. Okay? So watch what happens here. All right? On my graph, I'm going to turn off the circle just for a second. Okay? Because I want to figure out how do I sweep out this wedge of the cardioid. If I increase theta from pi over 3 to 5 pi over 3, what happened? Now, if you guys were walking in when Snyder and I were talking, this is what we were talking about. If I increase theta from pi over 3 to 5 pi over 3, I swept out the wrong part of the graph. You see that? I swept out the cheeks of the butt. And I don't know what the other part would be, but I need the back. Okay? If I made these my bounds, I'm going to get the area of these two parts. Okay? So the way to fix that is you need to have theta start here, down in the fourth quadrant, and increase to the first quadrant. There are two ways about going about doing that. Okay? One way is to start at 5 pi over 3.
So if I started at 5 pi over 3, and then I stop at pi over 3, pi over 3 is not going to work because that's smaller than 5 pi over 3. So I got to go past 2 pi, and that is, Samuel's about to say, 7 pi over 3. Okay? And now I've swept out that piece that I want. Okay? The other way to do that is to go from negative pi over 3 to pi over 3. That's also works. But you have to go from the fourth quadrant to the first quadrant to get that back half. All right? And then if I sweep out from 5 pi over 3, sometimes you got to be careful on these circles. 5 pi over 3 to 7 pi over 3 here. Then turn that on, I get the circle part. It will help you when you make your pictures or when you're doing your problems if you draw these lines in here. Because this, if I increase theta from there to there, that's that wedge. It's going to give me that whole area, including stopping right there and stopping right there. Okay, this is not area like that's bounded with the x-axis like it is in Cartesian. Totally different. All right? So then what's the area that we're looking for over here? How are we going to write that as an integral? I'll write it as 2. It's going to be the integral from pi over 3 to 7 pi over 3. Sorry, thank you. No. Yeah. Let me fix that. 5 pi over 3 to 7 pi over 3 of 1/2 r squared. So that's going to be the circle part. 6 cosine theta squared d theta minus the integral from 5 pi over 3 to 7 pi over 3 of 1/2 r squared, 2 plus 2 cosine theta. Okay? So this is the big chunk minus the little chunk. All right? And if you wanted to, you could combine these into one, and it would look like this. Or the integral from, and I'm going to change the bounds to use, who was the one that gave me negative pi over 3? Right? Oh, Alex. This also works, negative pi over 3 to pi over 3 of 1/2 r squared minus 1/2 r squared d theta. And if you really wanted to get fancy, you could pull the 1/2 out and just have that as r squared minus r squared. Okay? So both of these work. I mean, they look very different, right? But they both work. But I would not have you compute those by hand. I mean, honestly, like, if I were having you compute those by hand, like, the amount of time it's going to take you to do that one problem, I could give you 4 other problems. And, wow! I could give you 4 other problems that have you just setting them up that involve way more thinking and way more analysis. Okay? Questions on that? Okay, let's do one more. So our polar curve is r equals 2 plus 4 sine theta. Okay, and this is what's called a limacon.
embarrassing. So find the area of the inside loop. Find the area of the inside loop. So we'll first start off by setting r equal to 0 again, since I don't have two curves. And Billy's graphing it right now, I can see. Or he's playing Tetris. Hopefully he's graphing. So I get sine theta equals -1/2. So where's the sine negative? What two quadrants? 3 and 4. Where's the sine 1/2? In the pi/6 family. So theta is going to be, what's pi/6 in the third quadrant? And what is it in the fourth quadrant? So if you make your bounds, and Billy, you can check this, if you make the bounds 7 pi/6 to 11 pi/6, that's going to give you that inside loop. Okay? So that would be 7 pi/6, 11 pi/6, 1/2, 2 plus 4 sine theta squared d theta. Okay? So for homework tonight, I'll put this on the Google also. But you're going to do 7.4, 188 to 199, and number 212. Okay? You're just setting them up. This is going to take you some time also. Okay? I'm telling you, this is probably going to take you some time. Give it its due diligence. I guess that's it. On demand. Au revoir. Sayonara.